Good afternoon. Hello, hello, hello. Welcome to the virtual festival. My name is Freddie Mashate and I am your host. The virtual festival is presented to you by SciFest Africa, South Africa's National Science Festival, together with SAAO, South Africa's Astronomical Observatory, which happens to be celebrating 200 years of existence as an astronomical observatory today. It is this major milestone that has really led up to the collaboration between SciFest Africa and the SAAO, also setting aside October as a month that we celebrate space and astronomy. Let me take this opportunity to welcome Kirsten Gottschalk, who is from the International Center for Radio Astronomy Research, ICRAR in Australia. Kirsten is ICRAR's astronomy ambassador and manages their online presence as well as coordinate their outreach programs. Sorry about that. Her background is in astronomy and science communication and has a wealth of experience as a science communicator and educator. Today, she will take us through a workshop titled Engaging Astronomy, Resources for Educators and Parents, which is really designed to share some of the resources that ICRAR has been using to engage learners in astronomy. My hope is that we may be inspired to engage the South African learner in astronomy. As she is going through her presentation, should you have any questions, please feel free to send those questions or comments through the chat box if you are in Zoom. If you're on Facebook, please do the same on the comment section. We will be also monitoring that. Please do keep your videos shut and the mute button on so that there's no interruption throughout the presentation. Her presentation will have a break where some of your questions and comments will be addressed. Without wasting further time, Kirsten, thank you so very much for honoring our invitation. We are honored to have you on this platform and we are expecting to be inspired. You are the captain, the floor is all yours. Take us away.
Thank you, Freddie. I hope I can live up to that introduction. I'm so glad to be here with you all celebrating 200 years. How amazing is that? I don't think anything in Perth, Western Australia, is 200 years old, let alone our observatory. So I am so impressed that you guys are celebrating such a milestone. And I'm honoured myself to be here sharing what I've been doing over here in Australia. So thank you so much for joining me. It's this evening for me, but I understand for most of my friends in South Africa, it's about lunchtime for you all. So I hope that you've got something tasty to eat and thank you for joining me. So let me just quickly share my screen and make sure that you can all see my presentation. I'm sure Freddie will let me know if it's not working. I believe it isn't working actually. Here we go. Excuse me, everyone. Technical difficulties. It worked 3 seconds ago. There we go. Now we've got it. So, as Freddie said, I'm Kirsten. Hi. I work in Australia, Western Australia to be specific. I'll show you on a map where that is in just a moment. And as Freddie said, I'm the astronomy ambassador at ICRAR. I originally, back in a very long time ago, I won't tell you how long ago, studied astronomy at university and then promptly decided that I preferred to talk about it and teach it than actually do it. So I made a quick shift into science communication and education. And since then, I have been spreading my love of astronomy to anyone that I can trap long enough to listen to me. So thank you so much for being an audience for my passion and my joy this evening or this afternoon. So a bit about where I work. I've been lucky enough to work at ICRAR, the International Center for Radio Astronomy Research, for over 10 years now. ICRAR is a joint venture between the two major universities here in Perth, Curtin University and the University of Western Australia. And we're very lucky to be funded by our state government, which is quite unusual in Australia. Most science funding comes from our federal government, our national government. So we're very lucky that our state government funds us. And we exist because of an amazing project that you might have heard of, the Square Kilometre Array. If you haven't heard of it, don't worry, I'll tell you a bit more in a second. So my presentation today, I'm going to cover why you would be teaching astronomy to learners. I know in a lot of places in the world, particularly in Australia, also in South Africa, astronomy isn't a specific subject. Obviously, there are curriculum points that cover astronomy, but astronomy isn't an identified subject area for the entirety of schooling. So why would you look at astronomy resources and what are they used for? I'll also cover some general resources that are good for people of all ages, including adults and the general public. And then I'll focus in on some primary level specific resources and also some secondary level specific resources. So when I refer to primary, I'm talking for resources that are suitable up to about the age of 12. And for secondary, I'm talking about resources that are suitable from about the ages of 13 to 18. So first up, why astronomy? Why would we use astronomy with our learners? Why would we be branching out from our strict curriculum points and what we want to be teaching and talking about astronomy? I like to call astronomy a gateway science. I think that it's very hard to find someone who doesn't like space or doesn't like something about space. So you can use that hook of space is cool. People love looking up at space. They love learning about things in astronomy, and you can use them as that hook into other science and technology subjects. Astronomy in particular involves a lot of technology and a lot of innovation. Astronomers are really, really greedy scientists. They want to look further away. They want to look at more of the universe. They want to understand everything. And to do that, they need to be literally at the forefront of technology, building new cutting edge telescopes, working out new cutting edge ways to deal with the data that's coming from those telescopes. And so all of that innovation and technology means that there is a lot of really exciting stuff going on in astronomy that's developing new tech that has a lot of other applications outside astronomy. One of the more famous ones you might have heard of is that the program, the algorithm behind Wi-Fi that's in almost every device that can connect to the internet wirelessly was actually developed by a radio astronomer who was trying to observe black holes and figured out that instead of working out the exact great way to observe black holes with a radio telescope, that they created a program that would work really well for deconvoluting signals that are bouncing around within buildings and things like that. And so Wi-Fi was born. That's just one example, which I think we can take to the bank, given that everyone uses Wi-Fi. But there are many more. So in particular, one reason that I think that it's really relevant to both Australian and South African learners to engage with astronomy is because of the amazing technology and innovation that's happening because of this project, the Square Kilometre Array. So it's going to be the world's largest telescope. It's going to be breaking ground and starting construction next year. And it is literally at the forefront of both astronomy, but also engineering and computing science, because the dreams for this telescope are really, really big, and they are bigger than current technology. So they've needed to push the envelope in every area to make this thing happen. So where will it be? Where is the SKA? This little dot here on the map, this is where I am here in Perth, Western Australia. And the SKA site in Australia is that dot that just appeared there. So it's about, if I got in a car, it's about an 8-hour drive from the city of Perth. It's in a place called the Murchison. And then of course there is the South African SKA site up in the Western Cape, where this dot is. And then the headquarters of the SKA are in Manchester in the United Kingdom. So these are the three main locations on Earth that are relevant to the SKA. There's going to be part of the telescope built in South Africa, part of the telescope built in Australia, and then it'll all be run and headquartered from Manchester in the UK. And this is what it's going to look like in South Africa. So in the Karoo, these beautiful big dishes that are about 12 meters wide are going to be popping up in their hundreds. Not quite as easily as this animation. It will take a little bit to build them, but as I said, there'll be hundreds of these radio dishes in South Africa. And then in Australia, a little bit more unusual, might have seen in my background, are these, I call them Christmas trees. They work pretty much the same as your TV antenna does. despite looking like weird alien contraptions. There's going to be about 100,000 of these guys. And to give you a sense of scale, the dishes that were 12 meters wide, they're about 4 stories tall. These guys, these Christmas trees, they're about the same height as me, so same height as a person. So much, much smaller, but there'll be a lot more of them to make up for the size difference. So the SKA is described by the project leadership as one of the largest scientific endeavors in history, and it will bring together a wealth of the world's finest scientists, engineers, and policymakers to make it happen. And fortunately for South Africa and Australia, a lot of those world's finest scientists are going to be in our backyard, from our populations, from our amazing upcoming students and learners who are going to be perhaps interested in astronomy and using this telescope in the future. So whilst it's breaking ground next year, it's going to take a while to build 100,000 of those Christmas trees and a few hundred of those dishes. So it's going to take a while to get this telescope done. So your current learners are probably going to be the right stage in their career to actually engage with this telescope and use the data that's coming from it. And if you've perhaps got some older learners, they're going to be the right age to engage with the technology side, the construction side, the actual building of this telescope. So that's why astronomy, that's why learners should engage with astronomy and why you might be interested in the resources I have. Let's dive right into some of those resources and give you an idea of what you can start using. So underpinning most of astronomy is light. And as you might be aware, there are many different types of light, and they all come together in what we describe as the electromagnetic spectrum. And we find learners in Australia, they understand the concept of the rainbow and visible light, but when you start adding in the other types of light like X-rays and ultraviolet, they know about them in an abstract or even a real way, but connecting them all together as they're all just different types of light is something that they haven't quite made the leap to. So we've developed a few resources that really help take that understanding, that innate understanding of the colors of the rainbow and expand it out to the full electromagnetic spectrum of all the different kinds and wavelengths of light. So the first resource we have here, it's suitable for ages maybe like late primary through to adults. It covers concepts like waves, concept of a spectrum, wavelength and amplitude in minor detail, not really like the strong mathematical detail, but more describing what they are physically. And it is a video that describes it. So I'll play you a little snippet of the video. The full video is about 5 minutes long and goes through all the different types of light in the electromagnetic spectrum in detail, as well as how those different kinds of light influence us and are engaged with in science and in our everyday life. But I'll just play you a little snippet to start.
So when our eyes see red light, we're seeing light of a slightly longer wavelength. And when we see blue light, we're seeing light of a slightly shorter wavelength. In fact, the full rainbow is just different wavelengths of light that our mind interprets as different colors. Now this leads to an important question. What color is light with a longer wavelength than red? Now you will have heard of this light and experienced it all the time, but you just might not know that it's light. Because light at a longer wavelength than red is heat, or infrared radiation as astronomers call it. So when you go outside on a warm sunny day, the light that you see with your eyes and the heat that you feel on your skin is exactly the same thing, just at a different wavelength. What if we go to longer wavelengths than heat? Well, then we get to radio. So the radio signal that you pick up in your car is exactly the same as the light that you see as well, just at a much, much longer wavelength. In fact, just as your eyes interpret different wavelengths of optical light as colors, the radio receiver in your car detects different wavelengths of radio light and interprets them as sound. So in fact, when you're listening to your favorite song, what you're hearing is different colors of radio light.
So as I said, just a little snippet of that video that explains the electromagnetic spectrum. We find it's a really great intro to leap into a bit more of a wider discussion about the spectrum and how we engage with it in everyday life. We also find that it does lead to some interesting misconception busting, because a lot of people associate radios with sound, and then they're quite surprised to find out that radio waves are actually a type of light. They're not sound at all. So let me go on to our next resource, which is also about the electromagnetic spectrum. And this one is an interactive website where learners and students can actually engage with the electromagnetic spectrum and see how things astronomically out there in space might look differently at different wavelengths of light. So if we skip on to a video here that will just demonstrate this website for us. So it starts off this website with a little cartoon that explains the basics of the electromagnetic spectrum and the idea that there are all these different types of light. And there's also a link on the website that links off to the full video that gives more of a background. And then we scroll down to the actual interactive part of the website where students can engage with the actual spectrum. So there's two objects you can choose from to look at. You can choose the Crab Nebula, or you can choose the sun. And then you can use the drop down to choose which wavelength you might like to view the Crab Nebula in. Or you can press the play button and it'll play through all the different views of the Crab Nebula. So you can see here we're shifting to the infrared, and then we're shifting to the UV and down to X-ray and to gamma ray. And so some of them have videos because gamma rays tend to come in bursts, especially from the Crab Nebula, it changes. Then you can also switch to the sun and see something that's a little bit closer to Earth. And see all the different views of the sun in all of the different wavelengths of light. And then we also, down the bottom of the website, have everyday objects that are the same size as the wavelength of the wave to give learners a really concrete idea of how big is this wave. So radio waves are the size of a piece of paper, and visible light is the size of a bacteria. So giving them an idea of the different sizes of the waves. We also have a picture of the type of telescope that actually collects that type of light. And we also have an everyday object that is to do with that type of light. So that is our electromagnetic spectrum, electromagnetic spectrum interactive website. And I should say, there's a URL that you would have seen as part of registering that I'll also show at the end, and a link to all of these resources will be on that website for you after this. So don't feel like you have to frantically write things down as you're watching or go back to the recording. You will have a link to where you can get all of these resources, but this one's at spectrum.icra.org. So our next resource is another video. Now that we've talked about the electromagnetic spectrum, we like to go to what's near and dear to our heart at ICRAR, and that is radio astronomy and how radio telescopes work. So this resource, again, it's suitable for primary ages through to adult. And it goes through the kinds of concepts of how the waves come into a radio telescope, so like reflection, antennas, radio waves in general, and also how the data is transmitted from a radio telescope. So we find that radio astronomy is a bit of a foreign concept a lot, and given that it is a major science project in both of our countries, we feel that it's a really great way to engage students with something that they might consider as a career, given the boom that's happening in astronomy in both South Africa and Australia, by showing them how a radio telescope works. So I'll play this video for you and show you our animation of how a radio telescope works. One thing I really like about that animation is it shows the strength of the partnership between South Africa and Australia as the co-SKA sites to really sweep across the sky with the two telescopes and observe more of the universe working in conjunction. So that video there, this version's obviously in English. We have versions in another 8 languages as well. So it's a really international resource. So if you have learners that have other languages that they would prefer to learn in, we do have it available in other languages as well. So it can be quite a good way for learners to engage with radio astronomy. Our next resource is one that I quite enjoy. It's called Gleamoscope, which is perhaps a strange name. But it, again, is suitable for late primary through to adult learners, and it covers waves, spectrums, multi-wavelength astronomy, and even space archaeology, which is a really cool field where we're looking at the history of objects and things in our local galaxy and in space. And it's an interactive website as well, at gleamoscope.icra.org. And it basically provides you with a multi-wavelength view of the entire sky. So this is the screenshot here, but I'll go on to my video of Gleamoscope in action. So Gleamoscope starts and you're presented with the sky in visible light. The beautiful stretch of the Milky Way that's visible from the Southern Hemisphere. We're so fortunate down here to have this amazing view of the sky. You can zoom in and out and move around all of the different objects and see the night sky, perhaps if you had really giant telescope eyes. And then you can shift through different wavelengths and see the whole sky in all the different types of light across the electromagnetic spectrum. So you can start in the gamma rays and then shift into X-rays and then shift back through to visible light and then keep going down into the far infrared and then the microwaves. And then you end up in the radio wavelengths in a radio survey called GLEAM that was taken with a telescope at the Australian SKA site called the Murchison Wide Field Array. These objects here that I'm pointing out with my cursor, they are radio galaxies that aren't really visible in any other wavelength of light. So you can see in the middle there, the 2 lobes of a galaxy called Centaurus A. I'm zooming right in on it here. So this isn't visible at all to the naked eye or even to a visible telescope. Over in this here, there's a beautiful bubble. This is the VLR pulsar and some supernova remnants. So you get a really strong idea of all the different things you can learn by looking at all the different types of light and why we do astronomy across all the different portions of the electromagnetic spectrum. That one's a lot of fun as well, to have a look at the night sky that you might see above you and then what you might see with a telescope by looking at Gleamoscope and making that comparison, looking at light pollution. So you can bring an environmental aspect in as well, because obviously light pollution affects astronomy, but it also affects our wildlife and it affects our rhythms as human beings as well. So light pollution is a really interesting environmental and health aspect that you can bring in and engage with through astronomy. We've also turned Gleamoscope into a virtual reality experience, and it actually works on your phone. So it's a free app on your phone, and all you need is like a Google Cardboard or VR headset that you can slip your phone into. And again, it's suitable for learners from late primary to adult. I probably wouldn't have learners any younger than 10 using VR. There has been some research that's shown that it's not great to have really young learners using virtual reality. But again, the concepts here are the same as the Gleamoscope interactive website. But this one's even more interactive in that it has little objects in the sky that you can listen to information about and learn more about the types of things that are out there in the universe. So it's a bit more interactive even than the website. So as I said, it's available on your mobile. It's also available in Italian as well as English. And I have a few screenshots here. These are some of our audience members at our AstroFest in Perth and some of our PhD students using Gleamoscope. And then here are some screenshots of it. So it starts with the sunset at Australia's SKA site. And then as the sun sets, you're presented with the night sky above you in all directions, as a radio telescope would see it. And as you look around, you can see a full map of the sky in front of you that you can move around between, or you just look around and turn around in virtual reality. And you can see all the different wavelengths of the spectrum, just like in the website. And then you can also, as I said, pick out particular objects and read or have a voiceover explain to you what that object is and what you're looking at. And so this is really good for engaging learners with the different objects that are out there in space. The Australian curriculum, as you get towards the latter secondary years, does ask students to learn about galaxies and stellar evolution and concepts like that. And so with all of the objects that we've chosen to pick out in Caleidoscope VR, there is a wide variety of different objects there that start to bring those concepts out of that there are different things out in space. It's not just all stars. There are lots of different objects out there, and they all represent different physical processes. Getting towards the end of the general resources now. This is a resource we created because both of the SKA sites in both South Africa and Australia are really interesting places, but we don't want anyone to go to them, because if you go near a radio telescope, then chances are you'll have something with you that produces radio waves, and those radio waves will drown out the signals, the very, very faint, quiet signals that we're trying to collect from the universe. So because we don't want anyone to go to the SKA sites, but we want people to be excited about these amazing projects that are happening in their backyards, we've created a virtual tour of our site in Australia. So you guys, despite not being able to travel because pandemic, can take a virtual trip to Western Australia and see my extended backyard and have a look at what the telescopes look like that are being built in Australia. So the concepts here are things like radio frequency interference. So like light pollution in visible light, we also have light pollution in radio waves. We call it RFI. So those concepts are introduced. And that's why South Africa and Australia are the locations that the SKA is going to be built, because both of our countries are fortunate enough to have beautiful open space where there isn't many people living, where there isn't already lots and lots of radio waves that could be preserved by our governments as these radio quiet zones. So there's the Astronomy Advantage Zone in South Africa, and there's the Radio Quiet Zone in Australia that have both been protected to make sure that these places will exist to do astronomy from into the future. So this is an interactive website. Starts off with an overview of the entire SKA site at Australia, and then you can actually go and have full 360 views of pretty much anywhere on the site. So there's a little bit of overarching information at the top that kind of gives you a background in what's radio astronomy, what's the whole point of this site, what is a radio telescope, why does it need to be here in the middle of nowhere, what is this idea of radio quiet, and then you can launch into looking at all of the different things that are on the site in Australia. So this is our beautiful red dirt Murchison outback from a drone that flew up quite high into the sky. So you can see we've got some radio dishes that are a telescope called the Australian SKA Pathfinder, or ASCAP, that's managed and run by CSIRO, our national science agency. This is the large control building that actually controls all the telescopes at the MRO and has in it a supercomputer that collects all of the data from the telescopes. This building is shielded to make sure that none of the radio waves that are produced by all of this technology can get out and interfere with the telescopes. And then over on the other side of the site, we have the lower frequency telescopes, the ones that look a bit more like what the SKA in Australia is going to end up looking like. And we can see that there's all these different types of locations. You can zoom down to them and have a full 360 view of what's going on around there. So this is a nice way for learners to engage with a similar thing, but in another country, and get that international perspective on science and how science is done collaboratively and across many countries. and they can kind of compare the landscape in Australia to the landscape in South Africa because they're actually really similar. We've got similar colored dirt at our both sites, got similar vegetation. They look really similar despite being in completely separate continents. Second last general resource here. This one's a little augmented reality sheet information experience. It was on the, you could download this to try out yourself, list that I had on the website. The concepts here are things like scale, the engineering that goes behind the telescopes, the connection between the two different sites in South Africa and Australia and the differences and the similarities, and also the connection to the Indigenous Australians who are the native landowners of our Western Australian SKA site, the Wadji Yamaji people, and their strong and continuing connection to that country that's now going to be doing some amazing science. So how this one works is you have a printed sheet. Oh, if you can see that despite my background here. Actually, I might just turn off my virtual background if I can manage it to stop this cutting out the sheet. There we go. You can see my terribly messy room behind me. But here we've got our augmented reality coloring sheet. And the way this one works is basically learners or anyone can draw whatever design they'd like in the middle of the SKA dish here. And then when they use an app called Quiver, which is free on your phone, it's available on Android, it's available on iPhone. When they use that app to look at the sheet, you get a virtual reality thing pop up out of that piece of paper that takes your drawing that you've drawn on the SKA dish and puts it into an actual 3D dish in front of you. So I've got a few screenshots here of me doing a little bit of South African Australian connection because we both love the green and gold on the dish in here. And you can see there's the little SKA Australia antennas there, as well as the beautiful dishes that will be in South Africa. And I have a little demo that just shows the augmented reality side of it. Pardon the vertical screenshot, the app's vertical. So here you can see it pops out of the thing and you can watch videos within the app that explain what the SKA is. You can look at the scale between the two antennas and look at the differences between them. There's my hand behind to show you that it is augmented reality. This is the video that we have embedded. We actually embed the How Does a Radio Telescope Work video within the app. And then as you click on either of the antennas, it actually takes you to the overview of the world, and you can choose to go to the African SKA site and see different views of the dishes and see how they'll look when they're actually built in South Africa. In lovely 3 dimensions. And then you can pop over to Australia, if only it was that easy, and actually see how the antennas in Australia are going to be laid out. The fun one about this is the technology side as well, the fact that it takes the drawing that you've created in real life and makes it digital and pops it in 3 dimensions onto that surface of the dish. And our final general resource is one that's near and dear to me. It's one of my favorites, is our citizen science project that we do here at ICRAR. Again, this is suitable for late primary through to adult. We have teacher guides and curriculum resources for both late primary students and secondary students that touch on the Australian curriculum concepts, but they're general basic physics concepts that will also have connection in South Africa. The concepts are things like galaxies, digital technologies, and how astronomy works digitally. Science is a human endeavor, and the understanding that science isn't this necessarily A to B discovery without bumps and the human aspect of it happening along the way, as well as actually engaging in doing some science yourself as a learner. And it's available at astroquest.net.au. I've got a little screenshot here that shows what it's like. The whole idea of the project is that our AstroQuesters, our citizen scientists, create an account on the website, and they get shown galaxy images, and they take a look and they see whether the outline that's been drawn by a computer around that galaxy is correct or not. So it's really important for astronomers that have lots and lots of data from millions of galaxies to know exactly where the edges of the galaxies are, so that when they're trying to work out how much light is coming from that galaxy, what wavelengths of light are coming from the galaxy, so they can see things like how far away it is, how old it is, whether it's making new stars or whether it's stopped making new stars. They want to make sure they're only using the light that's from that galaxy and not from anything else. And computers are generally pretty good at finding the edges of galaxies, but they fall down and fail about 10% of the time. And with millions of galaxies, astronomers don't have enough time to look at every single picture and work out where the computer's got it right and where the computer's got it wrong, which is where the citizen scientists come in to say, hey, does this look right? And if it doesn't look right, what's wrong with it? And if it does look right, tick, great, use the computer. And then astronomers can go in and look at the galaxies identified by the citizen scientists as being wrong and fix them up. So head on to astroquest.net.au if you'd like to help us out with some of our science. I might pause here at the end of general resources and see if anyone has any questions they'd like to ask, or we can take a bit of a breather and a stretch, and I'm going to have a little sip of water while Freddie sees if there's any questions from you lovely listeners.
Well, thank you very much. I'm inspired. I want to be an astronomer right now. Hey, please, if you're watching, use this platform to engage with us. We really want to hear what you think. If you have any questions, if you're on Facebook, write your comment on the comment section. We are also monitoring that. But I also have questions of my own. Kirsten, how important has it been for especially learners to engage with these virtual platforms, and what is the role of teachers and parents? What have you seen to be the role of teachers and parents in this process?
Obviously, we're in uncharted territory at the moment as educators, as parents with our learners. We've gone from the tried and true ways of engaging our learners face-to-face to having to deal with them through computer screens. We're extremely fortunate in Western Australia at the moment to be doing really well COVID-wise, and we know that a lot of other countries, including South Africa, are really struggling still. And so there has been a very big shift globally to engaging our learners online. And so having digital tools like the ones I've presented are just so important to enable learners to take a breather from perhaps the video call style of teaching that's trying to emulate the classroom look and feel, and give them a chance to engage something at their own pace a little bit. We find all of the tools that I've introduced so far are really useful ways for kids to have a little bit of fun and engage with something that they might not feel like they're necessarily having, knowledge shoved at them. And then you use that to then scaffold around and bring the concepts in and be like, oh, remember when we were talking about this? Well, that's actually coming into play in this resource here. So, when we talk about ultraviolet light, or when we do, some experiments to do with waves, and we discuss waves and how light bends and things like that. Well, that's how telescopes work. The light comes down, it's reflected, and it gets bent up. And so you do these activities and then scaffold around them to hit your curriculum points. And so you can still do the digital engagement, but as I said, it gives kids that break to do something at their own pace that is online, that they can engage with separately, and then they come back. So I don't know about everyone, but I get a bit of Zoom fatigue if I'm on a video call all day. And so we've found it really useful when doing activities online to say, all right, everyone go and play with this website for 10 minutes, have an explore, and then we come back and we say, oh, what did you find? What was interesting? Did you see this cool thing? And discuss it and then scaffold around it.
Oh, wow. And just out of interest, I mean, you use a lot of animation, and you mentioned cartoons at some point, and my imagination is that especially young learners, they have interaction with this, animation and cartoons from a very young age. Has that been very successful?
Yeah, well, I find, especially when we're going to give presentations in schools, that kids they love to watch a video, even if it's you in the video on the screen. They'd much rather watch the video than have you talk at them for the full 30 minutes. I don't understand why it happens, but it seems to just really spark that attention back again. If perhaps the talk wasn't engaging them, even though you're making it interactive and you're using all of your learning tricks that you have, your teaching tricks. I find just popping the video up, popping the animation up, just does that reset, like having the digital experience does as well. And it kind of has that separation effect of it's a different authority speaking. So, as an educator, you're the one who's, seen as the authority perhaps, and you're helping the learner engage with what you're trying to teach them, and you're helping them along their learning journey. But having an animation or video brings in a different authority and a different voice to explain the information. So again, I really like when I'm teaching to use the animations as they are, and we've kind of designed them to not be super detailed so that you can show them to a young audience and kind of leave it at that and be like, did you see the pretty colors in the galaxy? Or you can then take it to a middle school audience and really discuss the reflections of the waves, and then do an experiment that uses lenses or mirrors to concentrate light rays. And so you can really build on it and use your then teaching to the right level for your students after you've kind of introduced the concept or used the animation as a different authority.
Yeah, excellent. We have a question. Our audience have started to interact with us. Really exciting. We have a question here from Neville Young, and they're asking: have you noticed an increase in data traffic at the ICRAR at the ICRAR website during lockdown period?
We have, definitely. So not just with ICRAR, we have a network here in Western Australia called Astronomy WA. That's all of the astronomy education and outreach providers in the state. And all of our providers have noticed a real uptake in engagement during the pandemic period. Our local observatory, the Perth Observatory, they started doing online observing evenings twice a week, and they had a great audience logging on to their Facebook Lives that had views through telescopes and tours of the observatory and things like that. So we've just definitely noticed a big uptick in the engagement with our online resources, but I think that's pretty standard across anyone that has anything online at the moment, because everything's just had to shift so much.
Yeah. I'm interested to know, just as a follow-up, Australia, I think this is something that many people might be thinking about, because in South Africa, we have, a huge digital divide. Is that a thing in Australia? Do you have to deal with it? Are there sectors of, your society that also have, challenges with accessing data, and how, have you dealt with that?
Yeah, no, it's exactly the same in Australia. I think it's a consequence of the wide open spaces we have in both our countries, and this population spread, as well as the inequalities that exist between different populations. So it's definitely something that we see in Australia as well. And it is something that our government is definitely trying to address. They're pushing hard, especially for more remote and regional schools in Australia, to have a boost in their technology capability and their internet connection. You might have heard of our national broadband network that was started, I don't know, almost a decade ago now, with a goal to have 99% of Australians have access to a broadband internet connection. That is almost there, but the connections can be quite shaky, particularly to our remote Indigenous Australian communities. And so it's not something that we found ourselves in a position to address specifically as ICRAR. We wish we had the resources to help bridge this divide, but the way that we strategize to still engage with those groups is we work with groups within our universities that actually travel out to our remote and regional communities and go there in person. And we were lucky enough even recently, to be able to travel regionally within Western Australia because of our situation in the pandemic. And so we've been and done regional school visits recently, but when we were in the full lockdown period, what we were doing is actually sending resources. So sending USB drives with all of the resources on them, and then helping teachers over the phone if they needed the help, and trying to bridge that divide in that way. Because, you know, okay, you don't have the broadband connection to watch all of these videos on YouTube. No worries, we've got them all in high resolution and we can post them to you.
I think one great thing that I can just remember that was happening here in South Africa is at a school, Rhodes University, they had students that were actually putting some of those resources in an SD memory card, and that you can just pop in your phone, you know, and that makes, you know, these resources available. Just to answer Pumza's question, Pumza Chebe, Miss Pumza Chebe, she has asked the templates for the worksheets available online. I think Kirsten had answered that to say every resource that you are, you know, showing during this workshop is available on your website. But just to ask, maybe
all on one individual page for you all, so you don't even need to go hunting for them.
Yeah, great. But just to ask, you know, as we round up so that you can get back, you mentioned something that, you know, you said your older learners, they can be involved through, you know, construction, engineering, etc. And you mentioned that young learners, you know, will most probably be well suited to read some of this data that will be, you know, coming through via these telescopes. I think a question that might arise, do you need to only study astronomy for you to be involved in this great big project?
Not at all. And in fact, right now, the astronomers don't have much to do yet. They're still in the planning stage for when the data starts coming. All of the work for the SKA at the moment is the engineering side, the computing side, the structural side, the policy side. So there are a wide swathe of careers that can be involved in the SKA. So from the technical side, from the trade side in the construction, through to the big infrastructure and engineering and electrical engineering side. So in fact, I would encourage, you know, almost any STEM field that's science, technology, engineering and maths has a connection in some way to the SKA project and can end up contributing. So there is heaps of capacity for learners that perhaps don't want to end up as research astronomers, but are interested in hands-on tactile engineering side to be involved in this mega science project as well.
Yeah. Kirsten, I see time is hating on us. So I'll allow you to just get back to the final segment of your presentation. Then if you do have questions as an audience or on Facebook, please send those through. We will address them. We are monitoring the comment section and the chat function in Zoom. Thank you.
Thank you. So my next resource is a little fun cut and paste activity to make your own little paper SKA dish. So there is a little download where you can cut out the SKA dish and then follow the instructions to build your own. The kinds of concepts that are here are what a telescope looks like, how it actually functions, radio astronomy in general, and then also the specific fact of the SKA that it's not just one big telescope, it's lots of telescopes connecting together to make one big scientific instrument, and that's what we call an array telescope. So this one is a PDF that you can download and you can actually build your own little SKA dish. Here's some examples of the ones that we've built and hung up around our displays and things in our office. So this is a nice activity that is really tactile, particularly for the younger learners who like to be doing something with their hands as you're talking about concepts and like to have a really concrete thing to discuss things. Plus it's super cute. You can make your own little array and put it in the grass in your backyard. So that's a really simple one that can talk about radio astronomy and start talking about the kinds of concepts that you might be talking about in primary school, like what's in the night sky and how the Earth turns and things like that, and talk about how telescopes move around and look at different parts of the sky. The next one is our scale solar system activity we have. This one's about the sizes of the planets. and it involves a whole lot of Play-Doh. So it's suitable for kind of late primary ages through to early secondary. So when you're actually looking at the 8 planets and their characteristics, the concepts are, you can talk about the gas giants versus the inner rocky planets and the relative size differences between the planets. We've got a PDF activity that has an instruction sheet for how to put it together. And I've got a short video that shows some of the actual activity being undertaken by 2 of our PhD students. So you start off with a big lump of Play-Doh and a ruler, and you cut it up progressively until you end up with all 8 planets at the correct scale compared to each other. So obviously our students here aren't placing the planets at the correct distances apart from each other, but you can see starting from Mercury in the middle, and then obviously you've got giant Jupiter with the red spot that they've created in the middle there, and they're going and putting Saturn. And so you can see the relative sizes, because we find particularly younger learners have a vision of all the planets that Earth is like this big compared to Jupiter, when obviously it is not. It is significantly smaller than Jupiter. So this helps with a really concrete, not abstract way of students understanding what the scale is between the planets. And then, of course, you can discuss mathematical concepts like scale models and things like that. So the instruction sheet is on our website. It's just a PDF, goes through step-by-step instructions for your lesson plan of how you might do it. This is a really great one to do at home. I've actually done this one with my 3-year-old in that I did it for her and we just discussed the different planets, and she had a great time smashing the planets together and squishing them. So you can use it with younger learners, just adapting it and making it more about, oh, let's talk about how there are different types of planets. We also have a different type of scale solar system that we use, and this is to do with the distances between the planets. So that other one is the sizes, and that uses Play-Doh. This one is the distances, and this one's also pretty low resource. It uses a very long piece of string and then something to mark the planets. So it's again suitable for late primary to early secondary, mainly in terms of the concepts it teaches. But I actually did this at a early learning center just a few weeks ago with some 3 to 5-year-olds. So you can again adapt it for the younger audiences and younger learners. And the concepts here are the distances between the planets, showing how the inner planets are grouped together more, and then the outer planets get further and further away. You can start talking about space exploration and how we have sent probes to other planets and things like that. So you can just bring in all of these different concepts as you're actually going through this activity. The way I like to do it is I lay out a big string, or a rope, I should say, that's 30 meters long. And I use a scale of 1 meter equals 1 astronomical unit, which is the distance between the Earth and the Sun. So the Earth will be at 1 meter on that scale. And then I place down Mercury, Venus, Earth, and Mars for the students, and I show them and we discuss how they're all quite close together, that these are the terrestrial planets, the rocky planets. And then I get learners to guess where Jupiter is and to stand along the rope where they think Jupiter is. And invariably, they all stand far too close to Mars. They never get it right. And then you step out and put Jupiter where it actually is, and then so on to Saturn and Uranus and Neptune, giving learners an idea of just how far apart the outer planets actually are. And so as the students are walking along, you can see these students here, they've left Saturn behind and they're walking along to Uranus and Neptune. This is the 3 to 5-year-olds that I did this activity with just a few weeks ago. You can see me taking big, giant 1 meter steps out to place Saturn, and they're all watching. As you go along, you can start talking about why the planets have the different characteristics, why Neptune is cold. Look how far away the sun is. That's why it's cold. Why is Mercury hot? Oh, it's really close to the sun. And start bringing in all the different concepts of the different planets and their names, and you can even start bringing in the mythological aspect of why the planets named what they are, what are some of the local stories about the night sky and the planets, so you can really bring culture into it as well. So this is a really great variable activity that really has that basis in the mathematics, it has the basis in the STEM and the planets, but you can really go all out with it and expand it out. A really nice extension I like to do with this is adding some art to it, making it a STEAM activity, and actually having the kids paint their own planets with polystyrene balls and then placing those planets along the rope with me once they've made them. We also have a really great activity that delves a little bit outside astronomy and into the other fields that are really related to the SKA, and that's the computing. This one's called Cosmos Computing. And again, it's suitable for the late primary through to early secondary ages. This one isn't as adaptable to do with younger kids. You probably want to be doing this with like 10, 11-year-olds at the youngest. The concepts that are covered are how computers work and what all the different components within a computer do. The fact that a code or a program is just a set of instructions, and that computers are dumb. They can't do anything for themselves. They need to be instructed what to do. And how it works is there's a full lesson plan, discussion points, and all the student sheets on our website. But basically, students work in groups of 4 to role play the different parts of a computer. So one person is the CPU, the central processing unit. One person is the arithmetic unit. I can never say that word, I'm sorry, that does the calculations. One student is the hard drive and one student is the display, the screen. And they all work together to go through a program and end up with a picture on the display on their screen. And this is what a program looks like. This is the basic one that we use as a starter to get students starting off. So basically the CPU has this program. They instruct the arithmetic unit to add 6 to X and add 3 to Y. And then they ask the hard drive, what is color 15? And then they tell the display, all right, if X is 6 and Y is 3, color it in the color of color 15. And then you should, all things going well, end up with a smiley face on your display. And we find that this is really great for learners because they immediately start realizing that the way that they start doing it is really tedious, it's really slow, it takes a while, and they start taking shortcuts and they start making it efficient. And they start, so the CPU starts remembering, okay, color 15 is yellow, I don't need to ask for that again to waste time because the hard drive has to flip through this book to find color 15. And so they start inventing all of these solutions to make it easier for themselves that are actual things that happen in modern computing. So things like, oh, I remember what color 15 is. That's a cache like you have on your web browser. And we have a nice sheet that goes through some of the things that kids might invent and then what their actual computing equivalent is. And so we find learners really love this because they feel like they're cheating and getting away with something. And then you say to them, well, you know, you actually invented something that's really important for how computers work these days. And they really enjoy that. We have a few programs there that you can use, like this Minecraft pickaxe and things like that. But we also have an online tool where you can create your own program. So you can draw a picture and then it'll give you the program to be used in the activity. So this is a really great activity for differentiation. So you can perhaps do your learners' initials, or you can do something that you know is really interesting your learners at the moment that they're a bit obsessed with. We did some Pokemon Pokeballs during the Pokemon Go obsession a few years ago. So you can really adapt it for your learners and their interests by using the online tool. And we find this one's a really great intro to then kicking students off to using all of the online coding learning tools that are out there. So this kind of really gives them that base level grounding without any needing access to technology needed in how a computer works, that then they can have this innate understanding of what they're actually doing when they're building code. So I'll head on to now our resources that are suitable for secondary students. As I said, when I talk about secondary, I'm talking about the age 13 and up level. So we have, as part of our AstroQuest Citizen Science project, you earn rewards as you do more science for us. And one of those rewards are you earn trophies that are associated with these people we're calling our cosmic champions. And they are historical astronomers up to modern astronomers that are really diverse in both their backgrounds and the types of astronomy they've done, to really highlight perhaps some underrepresented people or overlooked voices in astronomy's history, as well as acknowledging all of the really meaningful contributions that individuals have made to the field. So this is a really great way to introduce the diversity that exists in science, and how science is done and has been done in the past to learners. And the way we do that is we've got our 30 cosmic champions. And at the moment, we're almost done, which is why I can't show you the activity, but we will have it ready in the next few weeks. We're working on a few different lessons that actually use the cosmic champions. One of them's in a bit of a game of Guess Who, if you've ever played that game, where you're flipping up the faces. It was something that was integral in my childhood in Australia, but I'm not sure if it's as prevalent in South Africa. But it's kind of like a Guess Who type game where students work in pairs to guess who the other's cosmic champion is. And so these are just a few of the examples of our cosmic champions. We have Annie Jump Cannon, who was one of the Harvard computers, the women that Harvard used to be people brain computers, actual human computers, and look through photographic plates of the sky and classify visible stars and create catalogs. And her work was not recognized at the time necessarily, but now she's recognized as being instrumental in the development of contemporary stellar classification. We also have Arthur B.C. Walker Jr., who was an African-American solar physicist who pioneered both ultraviolet and X-ray observing. And we have, I always say this wrong, so please excuse me, I think it's Hypatia, and she was an Egyptian astronomer from Alexandria a very long time ago, in the year 360. And she was, she constructed some amazing astronomical and other scientific instruments, as well as improving the current best theories of astronomy. We also have Katherine Johnson, who was one of the first African-American women to work as a NASA scientist. And she was one of the women who was made famous by the movie Hidden Figures, if you've seen it. She was an absolutely amazing woman and very important in the history of astronomy and space exploration. And Vera Rubin is an amazing woman. Sorry, I should say was an amazing woman. She unfortunately passed away a few years ago. She actually essentially discovered dark matter, this thing that we don't fully understand. She was the woman who basically noticed the issue in the rotation of galaxies to discover dark matter. So we have 30 of these. I've only shown you 5 here. And we have biographies and information about these famous astronomers, or perhaps not as famous, but we think should be famous astronomers, that look at the diversity of cultures and input into our field over time. We also have, perhaps for a little bit of fun, I like using these when you've perhaps got the end of an afternoon, or it's the end of a teaching period, like a term or a semester, or it's Friday afternoon and your learners are just done with the week, they're done with the year, and they just want something that's perhaps a little bit fun, that they can fill out, that they can just engage with at their own pace. And that's our educational activity sheets that we created in conjunction with a newspaper here in Western Australia. So these are really good, again, late primary to early secondary. And they cover the history of science, solar systems, space exploration. They were created to celebrate the 50th anniversary of the moon landing. So there is information about the moon landings in there. They're all available online as PDFs, including answer guides. So there's 3 different little booklet sheets. One is about our place in space and us looking up at space. The next is about looking out far into the far reaches of the universe with astronomy. And the final is about the moon landing and the whole history that happened there 50 years ago. So to give you a little taste of the kinds of things that are in them, there's activities like naming the planets, look this up, create this thing, read this, let's have a little match space terminology to pictures. There's word searches and things like that. Just those little fun activities that you might want to use as a little bit of a break or a little bit of a an opportunity for learners to really consolidate their knowledge that you've been teaching them using other methods. So yeah, little word searches and things like that. There's also some really nice activities that bring in the English and writing skills, like persuasive writing, or looking at the for and against of some issues and things like that that are to do with space and astronomy. So this one here in this sheet is the animals in space, and do you think it's ethical to use animals in space exploration, and having students really consider that issue. And then, yeah, lots of different little mini activities and information about astronomy. Next, we have our Weighing a Galaxy series of activities. This one, we've created two differentiated sets of activities for two different ages. So we have versions for year 8 to 9 in Australia, which is about the 14 to 15 years old. And then for years 11 and 12, which is the final years of schooling here, so 16, 17, 18 years old. So the different levels of ability in the mathematics basically is the difference between them. The concepts here are really drilling down into the composition of galaxies, such as stars, gas, and dust. And these are curriculum points that are hit strongly in year 10 in Australia, in the Australian curriculum. We also look at galactic rotation, Hubble's law, redshift even, as well as using those algebra and mathematical and calculation skills and making meaning from graphs, as well as looking at dark matter. So what we have is a set of PowerPoints and worksheets and the solutions for you to use as a lesson. I'll give you a bit of a taster. Basically what the lesson does, it introduces the concept of what is a galaxy, what are the parts of a galaxy, and then we look at a visible light image of a galaxy. And then we also look at radio data from that same galaxy. And we use those two pieces of information to actually work out how much the galaxy weighs. So the PowerPoints have, from the beginning, you know, the concepts of what the galaxies are made of, talking about a radio spectrum and what it looks like and why it has the shape it is and what information it's actually giving us. Also talking about, you know, the shape of it and why it's shaped that way, and all leading up to doing some maths in the worksheet using Kepler's laws to actually work out how much the galaxy weighs. So really, basically all you need is a calculator and those two pictures, and you can actually work out the mass of that galaxy. So as I said, we provide all of the solutions and all of the activities there. We find that this one is really good for later year physics students who are using these concepts and learning how to do calculations. And it's also a really nice way to introduce dark matter, because once you weigh the galaxy, you discover that you actually have too much mass in the galaxy compared to what it looks like. And so all of that extra mass is that dark matter. And finally, our final resource, and this is perhaps save the best for last, is a resource that we absolutely love. And these are actually our telescopes that we have, that are research grade telescopes that are connected to the internet that students can use. So they are suitable for secondary students, and some adults do use them as well. So we use them in our tertiary education at university and some adults, and we actually do research with these telescopes as well. And the concepts that you can cover with these telescopes are very wide, but the ones that we have activities and lessons for are optical astronomy and creating images with a telescope, looking at how the night sky moves and planning, observing targets, image processing. You can even do light curves and photometry with these telescopes. They're fully interactive, and they require the learner to actually drive the telescope, or they can also request images get taken for them. All the information about these telescopes is at spirit.icra.org, but I'll show you some imagery of them. So we have 4 telescopes currently, and by I think the middle of next year we will have 6 telescopes, because we are expanding. So we have 2 telescopes in domes on the roof of one of our buildings at our university campus in Perth, and then we have 2 telescopes up at a dark sky observatory site about an hour-and-a-half's drive away from the centre of Perth, which is getting pretty regional if you're in Australia. They're all really beautiful big telescopes, 35 to 40 centimetre mirrors with beautiful, cool CCDs on the back of them that can take really nice images. There's a little video of the 2 telescopes that are up at our dark sky site doing their morning exercise wake-ups. So these telescopes, as I said, they're all remotely connected to the internet. They're all able to be used completely remotely from anywhere that has an internet connection, and students can develop a plan for what they'd like to look at and then end up with some really beautiful images like these ones. So all of these images I'm about to show you were taken with the Spirit telescopes. This is a globular cluster, another globular cluster called Omega Centauri. Beautiful planetary nebula, Andromeda galaxy, the moon, quite a beautiful image of the moon, beautiful image of the Orion Nebula there. Some really nice images come out of this telescope. And then there's a selection of galaxy images that are created with the telescope as well. So you can see what I mean by research grade telescope, where you can create these beautiful color images. So we use this telescope predominantly for some programs that we have the aim to increase a student's self-efficacy, which is a very educational word that I'm using, but it basically means increase a student's view of themselves as being capable of STEM, being a capable scientist, being capable of doing things like astronomy. Because we find that there is a divide with the areas of people that are underrepresented in astronomy. So in Australia, we find that is Indigenous Australians are underrepresented, women and students from low socioeconomic backgrounds, they're all underrepresented in astronomy. And we want that diversity in our field. And so it's not about encouraging those students to say, STEM is amazing, do STEM, because we find that we're losing these students because they start to hear this message of, you're not good enough to do this, you're not smart enough, you're not capable. But it's not true. They are capable, they are able to do it, but they need to build their confidence in their own ability. And so we use the telescope to show them that they're doing some real research grade science with this real professional instrument as part of their class in high school. And students end up creating these beautiful images and see the result of what they've done, and then learn how to improve it and grow that confidence and that self-efficacy that might then, tweak the light bulb of, well, I never really considered working in a STEM field, but now I know I can if I want to. So they might start considering it more. So that is a whole lot of resources. Thank you so much for listening. As I said, I'm going to put a link to all of these resources up on that website. I'll do that for you tomorrow. So you'll have them all available really easily. I'll also put a link to this presentation there. So if you wanted to go through and see what age groups I put things under and things like that, this presentation will actually be linked from that website as well. And you are, of course, also very welcome to send me an email and ask me any questions. We'd love to hear from you and engage with you. There's such a strong connection between South Africa and Australia because of the SKA, and we'd love to work together.
Mute. Oh, wow. Thank you. I was just trying to unmute. Thank you so very much. As I said earlier, I think that time was our hugest enemy. And we're running, short of time. I think we have another session that starts at 2, and I understand some of our audience might be registered for that session that starts at 2. But I'm just going to ask one question, then we round up, because it came from Paul, who was watching, I think, from Facebook, and he says, how do you guys deal with air traffic radio signals in Australia to mitigate the risk in your observation?
It's an excellent question, because anything flying over the SK sites is an issue. And it's actually been set up so it's a no-fly zone. So we're lucky in Australia that Western Australia is very, very empty given how big it is. So there aren't many flights that would need to go straight across Western Australia over the SK site. And so basically the flight paths get diverted around it. We do get some interference from satellites going overhead, but luckily that's not major, and the telescopes can A, make sure they're operating not in the same frequencies as the satellites, and B, we make sure we're looking in different directions than when we know the satellites are coming over.
Wow. Thank you. I mean, Kirsten, this has been amazing. I am prompted to just round up a little bit, just to tell our audience, thank you for sharing this time with us. The resources that you were giving, Kirsten, they were really, really helpful. I was glued myself. In South Africa, we have this saying or this principle that we celebrate that is called Ubuntu. And you can easily equate it to sharing is caring. And today what you have done is to empower all science engagement practitioners. I mean, I'm speaking of science centers, I'm speaking about our educators and parents to inspire the South African learner. Thank you to you, thank you to ICRAR. And with that said, it is just time to say goodbye. Please do visit our website for other programs that we are on offer. There is, especially over the next 4 days, with AstroFest kicking off today in collaboration with SciFest Africa, our 6 months program also running. Please check our website so that you can see other events that you can take part in. Kirsten, do you have any last words that you'd want to leave the people with?
Just to say thank you so much for joining me, everyone. I hope you all stay safe. We're sending our love and support from Australia during this terrible time for the entire world. And I'm so happy that I could join with you and celebrate AstroFest. Thank you so much for having me.
Thank you. And if everyone could put on their camera so that we can just wave and say bye. Thank you very much for joining us, and we will be seeing most of you in some of our other activities, I hope. Bye-bye.
Bye-bye.
Bye.
Thank you.